Right, in the last video in part one of partial sums of a series, we learned what a sequence is, a series is, or reviewed those, and then we looked at the idea of a partial sum of a sequence, and we were able to conclude that we can make some statements about convergence or divergence based on the convergence of this partial sums. So the first exercise in the text is simply asking us to evaluate the first four partial sums of a couple series here. So just to point this out, the first thing you need to do is generate four terms of the sequence itself. Then you need to generate the partial sums. Notice we add the first two terms to get sum 2. We add the first three terms to get sum 3, and so on. So adding up all those numbers then, the first four terms of the sequence is given by the U set, but the first four partial sums is given here. So again, that's in terms of vocabulary. The second series of exercises is write an expression for the nth partial sum. This is something they'll only be able to do with you now if they're giving you an arithmetic or a geometric sequence. Both of the examples here are arithmetic. But I just want to point out that we can still do this. So in this case, I find out that the list U sub 1, U sub 2, U sub 3, and U sub 4, I've got all four of the first terms of the sequence, but then the partial sums themselves, S sub n, I'm skipping some steps here, but obviously S sub n is going to be the first term plus the second term plus the third term all the way up to the nth term, and the nth term is given by the expression itself. Once again, we recognize this is an arithmetic sequence because 1/5 is the common difference between these two. Or would it be, I think it's negative 1/5, of course. But we don't worry about the common difference here because we have the first term and the last term for the sum of an arithmetic series, n divided by 2. So we put in the first term, 9/5, we put in the last term, and then we do some cosmetics, clean it all up. And always know, as we know, the limit as n approaches infinity of this quadratic is also not going to 0. In fact, it's going to infinity. So the series diverges. Since the limit as n goes to infinity is not equal to 0, then we can assume the series will diverge. So it's pretty straightforward. The last set of skills that they have to build, and again, all of these are skills to build on. We're going to need to know the language, and we need to know what they mean when they say partial sums and converge and all these other kinds of things. So here's another sort of skill that the authors want you to be clear on, and that's finding an expression for the, given an expression for the nth partial sum, can we find U sub k? This showed up in a test question in the core curriculum at one point, but the notion here is this. S sub k, of course, is the sum of all the elements in a sequence up until the kth element. S sub k minus 1 is the same sum, less the kth element, but it does contain the one element before the kth element. Naturally, if I subtract these two, we're going to have the first set of sums, or the first sum, and the second sum subtracted from one another. As you can see, U1 subtract U1, U2 subtract U2, and so forth. Everything is going to subtract out all the way up to the k minus 1 term, leaving us with just U sub k. In other words, U sub k can be found by taking the difference of consecutive partial sums. So this is a lot of highfalutin mathematics simply to say what most of us can intuit, and that is if we took the 7th partial sum and then we took the 8th partial sum and we subtract them, we will get the U sub k term because we've added U sub k to get there. So using this information to find the U sub k term, here we're going to take S sub k, subtract S sub k minus 1, which is shown here. And subtracting out the 5s, we get this. And the rest is algebra skills. Multiply top and bottom by 4 so we can get a common denominator. And since we have a common denominator, we get that. So the U sub k is negative 15 over 4k. So that's the general term of the sequence that produces the partial sum formula shown there. So you could verify this, of course, by picking a value for k, like let k equal 5, and then you can find the first 5 terms find the fifth partial sum, and then see if the formula that was given here gives you the fifth partial sum by just putting in 5 for n. And that would be convenient. Anyway, one thing else I want to remind you is the difference between series or sequence again and the partial sums of that series related to the sequence. So here, for example, we've got the orange and the red, where the orange represents the sequence that was given, and then the red represents the partial sums. They share a point at first, but the partial sum goes up as the sequence itself continues to decrease, because in the first case, I've added the area of 1 times the value of the function. And so however tall this is, that is added to my partial sum. If that doesn't make sense, let's look at another example. This height right here, representing the area of the next rectangle, is added to our partial sum right here. This little bit right here of u sub 5 is added to the previous value before it, and so on. So here we can see again, this is the sequence. It's a sequence of numbers that is decreasing, but the partial sums are increasing. In fact, the issue is, will the partial sums increase and stop at a certain limit, or will the partial sums increase and just keep on increasing forever and ever and ever? So the issue here then is, well, that's the end of that video. I guess I'm going to continue on later. Anyway, so just to look at section 3A, and you can find other examples, just to make sure, again, that you're really refining your understanding of the vocabulary, what's meant by partial sums and the like. Thanks for watching.